Hey everyone, thanks for joining this session. My name is Tian Sheng. I work in Intel as a firmware engineer. My main focus is on open source firmware solution such as Oreboot and SimBootloader. And today will be joining us will be my friend Andy, who is also working in Intel as a system validation engineer on FPGA, and also Ron Minnick from Google, who everyone already know who he is. Before getting started, let me share with you a real quick story. This project actually got started just 12 hours before the submission deadline when Ron asked me, hey, it would be great if you can try this on Intel FPGA instead so that the open source community will have more options available. And I said, why not? And later on you will see those incredible works that have been done by my colleagues, especially my friend Amil. He is a genius in RTL. Without his dedication, we couldn't have achieved what we have done today. So thanks, Amir. So in today's presentation, Enable OpenTitan on FPGA with Oreboot, we're going to cover four main topics. The first one, of course, we're going to tell you briefly what OpenTitan is. The second part is we're going to tell you what needs to be done on the FPGA side to emulate the OpenTitan properly. The third part is we're going to tell you how we use Oreboot as a de facto firmware solution in OpenTitan. Last but not least, hey, we got a demo for you. It will be a fun and interesting demo by my friend Andy. So stay tuned with us until the end. Who doesn't like demo, right? Okay, let's get started. So what is OpenTitan then? OpenTitan is basically a dedicated root of trust controller. It is a RISC-V embedded solution. While there's still no ASIC solutions available yet, everything you need to find about OpenTitan can be found in opentitan.org. From the design itself, to the specifications, and to the RTL source code for the FPGA. So it's a completely open source solution. Just go to the website and look at everything you need. And OpenTitan also provide all the basic security needs, such as secure boot, AP firmware updates, and cryptographic support. That's all you need to know for today's presentation about OpenTitan. So let me pass my time to Andy, who will share with you about how to emulate OpenTitan properly on FPGA. Here you go, Andy.
Hi. Intel is providing a solution to emulate the OpenTitan on an FPGA. You can select from multiple different FPGAs, of course, but we decided to go with the Intel Max 10 and the board being the Intel Max 10 development kit. It is small and portable, so you can bring it and work on it practically anywhere. And they are pretty cheap as well. Overall, it is a solid overall starter FPGA development kit to have. So I have a picture here, which is the OpenTitan FPGA implementation, and it is called the Earl Grey. This picture shows the block diagram of the OpenTitan Earl Grey, and it shows the IPs that are currently available for the OpenTitan. A lot of these planned IPs are already implemented by the OpenTitan developers. For example, as you can see, some of the memories are already implemented, such as the ROM and the flash, which you can already start using. Besides that, more IPs are coming, such as the random number generator, which is marked by the faded out entropy block. And some IPs are in the process of being validated, such as the I2C. Currently, we are in the process of implementing them piece by piece in the Max 10. So, moving forward, a little bit of a background on the FPGA platform example. So generally, you need about 4 things, which is the water tools. But the other 3 things are the things that is kind of like you can use it to any other FPGA vectors. So the 3 things are the RTL, the boot ROM, and also the pin assignments. So the RTL is the file which describes the hardware that you are trying to emulate, such as the IPs in the previous slide that we just saw just now. It is generally written in Verilog, System Verilog, or VHDL. The pin assignment is the file that specifies the connection between the FPGAs to the output on the board. Without it, the FPGA will practically not be able to communicate to the outside world. The boot room is where we put the boot room. And for our case, our example, it is where we place the Oreboot which my colleague will talk later. With the three of these files, the Intel Quantus tool will synthesize and compile a bitstream for you, and it will come up with a file in the form of with a format called soft, which is the extension for the SRAM object file. You can use this file and download it over a JTAG connection over any other configuration that is available on the Intel FPGAs to program your FPGA. So currently, the OpenTitan RTL is available on their GitHub repository and is currently being tested and designed for the Xilinx RTX 7. The good news is the OpenTitan developers wrote most of this RTL in a way that these RTLs can be readily ported to theoretically any FPGA vendors, which includes Intel. However, some vendor-specific IPs needs to be changed to use what is available on your FPGA design tools. In our case, one of our IPs that we had to change was the clock so that the design can work properly. Other than porting over the RTL, we also did some changes on the pin assignments. The current available pin assignments on the OpenTitan repository is based on the Nexus video board, which uses the Xilinx Vivado to generate the pin assignments. Since we are using the Intel Next-Gen development kit, which is a totally different board, we need to redo the pin assignments on the Intel Quantus tool instead. As an example that I placed on the slides right now, you need to map the pins correctly so that you can use the functionality to output to the UI correctly. Next, my colleague will continue with the Oreboot.
Once the OpenTitan bitstream is correctly working on the Max 10, we need to look at how to get software running. And the first step in getting software running is trying to figure out what firmware to run. Now, there are a lot of choices right now in firmware. We want to go with open source choices, and even then, we have a lot of options. Some of them are old and some of them are new. One common thread is they're all written in C. So before we go much further into describing the decision we made for firmware, let's take a look at what firmware is supposed to be doing. Here's a very simple view of firmware. You turn on the CPU, it powers up, various things are ready, and then it fetches its first instruction. At some point, the CPU is finished initializing hardware, including the CPU, any buses, any memory, and then it's ready to select and run a boot media and provide runtime services. But OpenTitan is an embedded chip, and embedded chips come with many constraints. In many cases, embedded chips might have only 8 kilobytes of memory. OpenTitan is a little bit better. It can have 64 kilobytes in the current Earl Grey design. Further, however, ROM is far larger than RAM. In OpenTitan, we anticipate 512 kilobytes of ROM and 64 kilobytes of RAM. Contrast that with a typical laptop, which might have 16 megabytes of ROM and 16 gigabytes of RAM. Things are very different in the kind of environment we envision for OpenTitan. There's no way to communicate or diagnose problems. If a USB key like the ones we show crashes, it's just going to reboot. It's not going to really talk to us. It's not going to send a web form to show. It's not going to send a diagnostic report to a company. It's just going to reboot. So some sort of panic where it halts and waits for someone to do something is not in the cards. It's going to reboot on failure. Now, we don't want it to be constantly rebooting on failure. We want to have a very, very high assurance software, and that means we need a far more reliable language and runtime than C offers. We decided to go with Oreboot. Oreboot is a downstream fork of Coreboot with all the C removed. All the new code that was C is now written in Rust. The design is completely new. We preserve important parts of Coreboot's structure, including the directory hierarchy, many of the tools, and the assembly code. On the left, we have a notional view of the hierarchy of Oreboot components for OpenTitan and other boards. And on the right, we show somewhat how the code is assembled into a working image. So if we look on the left, the key structure, the organizing structure of an Oreboot port is a main board. A main board attaches a sock, the sock attaches a CPU, and the CPU attaches an architecture. So CPU layers on architecture because it may have specific implementation features that really are not part of the architecture domain. Sock layers on CPU because it comes with I/O devices, timers, that sort of thing that are not really part of a CPU implementation. Further, we have devices, including the Oreboot device of devices, which is a way of gathering up several devices into one function, and then, of course, physical devices. On the right, in the green boxes, we show that life begins in Oreboot with the boot block file, and that does very early initialization. It's assembly code. It very, very quickly flips into Rust. There are only about 10 to 30 instructions in a typical boot block. We have a link.ld to assemble things into a working image, and main.rs in the main board is where life begins post-assembly. Building is very easy. You clone a repo, you cd to a directory, and type make. All the Rust components you need will be fetched automatically, and after a few minutes, you're going to have a main board image that you can try and boot. The file is in the tree in the OpenTitan CRB directory a little further down under a directory called build, and it's named bootblob.vmem.
Alright, time for some demo. Let's go ahead and check the screen.
So first off, you want to download the Quartus Prime Lite Edition, which is free, and it is available in both Windows and Linux. You need this Quartus tool so that you can compile the OpenTitan design for the Max 10. So once you finish downloading and installing Quartus Prime, you can start compiling for the OpenTitan. First, you need to open up the project file, which is you click File and Open Project, and look up for the QPF file, which is right here. So I'm going to click that. As you can see here, the Max 10 OpenTitan design project is already loaded. I can click here just to see everything. So if you're interested, you can also look up the RTL file, and it can also open up inside the Quartus Prime Lite Edition. All you have to do is click on File and Open. So I'm going to my source. So these are all the IPs that is available on OpenTitan. So for example, I will open up GPIO, the RTL, and I'm opening up the top file. So you can see how the OpenTitan developers wrote the file if you're interested. Next is you want to compile for the OpenTitan bitstream file. So after you've loaded the project file, you click on the start compilation here, and it will output out a message that says it is running some the compilation tool, and you have to wait up for a few minutes. So when your compilation is done, you can check the logs here. Quartus Prime full compilation was successful. That means your bitstream file is successfully generated. So we can go ahead and check for that one. It's located at the same QPF directory. There's a folder called output files right here. So double click on that, and you can check here that you are looking for the soft file, which is right here. This is the file that you are going to use to program the FPGA. So this is the Max 10 FPGA development kit board. To use this board to load up OpenTitan, the first step you need to do is connect it to a power supply, which I already did here. The second one is for you to turn on the power button using this power switch right here. Next, you need to connect the mini USB cable that comes to the board, which is right here, and connect it to this slot right over here. This is the JTAG connection slot so that you can program the FPGA later. you will need to slot another mini USB cable right here for the UART output. So just slot them right on the side of the JTAG port, just like that. Alright, so once you are already done with the setup, you can now program the Max10. For that, go to the Portus Prime Windows and click on Tools, click on Programmer. For now, you want to click on this, right click it, and then delete it, and then press Auto Detect. Click OK. So there will be two devices here. Click on this one and right click on it and change file. So you want to go to the directory where your output files are located and then click on this soft file. Now you want to program it, so you want to tick this box, but before you configure, you need to set up a serial terminal or serial communication. For me, I'm using PuTTY, but you can also use Screen for Linux, for example. Set it up to the right serial line. For my system right now, it's on COM4, and set the speed to 230,400. I open that up, and now since this is done, I will program it. Progress bar 100% successful, and when I check back my PuTTY, the Oreboot is loaded.
Thanks, Andy, for the incredible demo. That's all we have today. We hope you really enjoyed the session. So just go to these few links to get further information about Oreboot and OpenTitan itself. We also appreciate if you can join the Slack link for the further discussion on this topic. And on the further related topic, there's another interesting sharing by Intel as well, which is another FPGA solution based on Intel Cyclone 5. So I encourage you all to take a look at that. That's all for today. Thank you again for bear with us until the end. Have a great day.
Hello. Okay, so I think we can say things now, is it?